different approach of formulating the equation of motions. Okay, and that approach is due to the conservation of the energy. So this will be the second approach for forming the equation of motion, and that is called the energy method. And forming the second one, determining omega n. Okay, so that method is using the energy method, and the energy method basically is this. So we consider, again here we consider is single degree freedoms. Single degree freedom, that means we can designate the degree freedoms in terms of its x, okay? And with that in mind, if we consider the system has a mass m and the mass of the system equal to m and the MEQ, the spring constant for the system, say KEQ. Okay, so with this information, then we can begin to formulate the total energy of the systems. And that is a summation of the kinetic energy plus the potential energy. Okay, and for single degree freedom, kinetic energy is very straightforward. Simply its mass multiplied its velocity squared. Potential energy, again MEQ, is the strain energy stored in the spring. Okay. So now this I want to know is let me say this is T. Okay, let me define the T is the total energy. Okay. I want to know what is the change of the energy over time during the vibrations. Okay, so this equation simply tell is, for me, the purpose of doing that one is I simply want to know the change in the total energy over time. Okay, and we see what happens. So simply it's d dt, and we put in here m eq x dot squared plus k eq and x squared. Okay, so that means here we take the derivative, and again we take the derivative on individual terms. If necessary, we need to take the chain rule as well. So for the first one, this will become MEQ x double dot times x dot. Okay, again, for the first term, I have taken into the chain rule. Again, there's a double derivative, the kind of whatever. And this is x times x dot. Again, for these terms, I have taken the chain rule as well, like this. You can double check, okay? This should be right. So that basically let me rewrite. Okay? Good. And what we can use, about these equations? Again, let me rewrite here. Is the total energy. Okay. So here, using this one, I'm going to impose these things for. Let me write here. For undamped system, we have the system description like this without any damping. So this is KEQ, this is MEQ. This is our degree freedom x. we know for this one, we have an equation of motion is MEQ dot plus K EQX equal to 0. We already know this. What we have done so far is to prepare ourselves for this, right? So this one, without any derivation, we just take it. With these things in mind, for undamped system, that means our derivative of the total energy equal to how much? 0. So for undamped vibration systems, we have a principle. That means we have this. If you are able to formulate the total kinetic energy and potential energy of the systems, you simply take into derivative. That will lead you right away into the equation of motion. Sometimes for some systems, it's easier to solve for it in terms of the energy viewpoint. Sometimes Newton's law will be easier, but that is the way we introduce here. And coming up Monday, we'll have more examples and continue to exercise this concept. And again, Monday, I'm going to show you how to use this approach to calculate this term. Thank you.